Let's take up the very first question. Normal neurons action potential, right? Now, the question goes like this. The channel being active at the star indicated segment in the given picture. Now, this picture gives you the idea here. The star is here, guys, isn't it? Which means the peak of depolarization and repolarization just begins, right? Now, what is the channel which is going to facilitate repolarization? It's a very simple question, but when it comes to the question that you're seeing here is going to be a little bit tricky. Now, of course, it is definite that there is going to be opening of potassium channels. Very, very, very clear. But you can see the options. Voltage gated sodium channel is given. That cannot be the answer. Rule it out. Since 2 is not the answer, 4 is also not going to be the answer. Rule it out. There is a possibility of repolarization by two kinds of channels. First, it is going to be leaky potassium channel. And the second one, it is also going to be voltage gated potassium channels as well. All right, people. There is also going to be voltage gated potassium channel causing repolarization, but both the options are given in the question. You got to pick one. If you got to pick one between leaky and voltage gated, since numerically leaky potassium channels are abundant, and that's the one which is going to bring about more amount of repolarization than the less numbered voltage gated potassium channel, 3 seems to be the best answer since you got to pick one. All right, so 3 is the best answer for the question, people. But in reality, this question has got both 3 as well as 1 as the right answer for the question, people. Please remember, it is not just leaky potassium channel alone. It is also about voltage gated potassium channel as well. Be aware of that, guys. Got it? Now, coming to question number 12. This is all about saltatory conduction. All right. Saltatory conduction, again, guys, we would have discussed this in classes. Saltatory conduction is nothing but the nodes of Ranvier. Every node of Ranvier is going to generate its own newer and newer action potentials. The reason why this is, the intracellular voltage keeps remaining positive. As a consequence, we have myelin, and myelin is designed to close the potassium channels. Since potassium channels are closed and covered, we prevent leak of potassium. We store all the cations inside the cell itself, and that is going to get the positive voltage conducting all throughout the axonal length, right? So saltatory conduction is genesis of action potential at each and every node of Ranvier, guys. We discussed the theory in the class itself. Now the question goes like this. Myelination of a neuron increases conduction velocity by saltatory conduction seems to be a right answer. Increasing axoplasmic conductance seems to be right answer. Decreasing axonal capacitance seems to be right answer. And hence, all the above seems to be right answer. The point here is, guys, option 1, option 2, option 3. All the 3 options increases a neuron's conduction velocity. All the 3 options increases neurons conduction velocity, guys. All right, but the question is very specific. Myelination of a neuron is going to increase conduction velocity by. Since the question is very specific about myelination, option 1 is going to be the right answer, even though 2 and 3 do increase conduction velocity. Because of myelin, only saltatory conduction is the mechanism with which the conduction velocity is increased, and hence option 1 is the best answer for this question. Increased axoplasmic conductance is mediated by axoplasmic viscosity. This itself is going to facilitate axoplasmic conductance. It doesn't require myelin. Decreased axonal capacitance is again because of a property of axoplasm and not myelin. And hence the right answer for this question is option 1, guys. That's question number 12. Factors increasing conduction velocity by myelination. Coming to question number 13. It's a sarcomere based question, people. You can clearly see all the bands and zones. The dark line that you are seeing here, these lines, the dark line you are seeing, it is going to be the Z line here, guys. Right, so these are all Z lines. These are all Z lines, people. And thin filament gets attached to Z line and everything. And the star is marked here. The star is marked here, guys, which means they are talking about I band, which is made of thin filament. All right. And the question goes like this. Identify the region indicated by star. It's simple. The answer is going to be I band, guys. Now, the black one here, this black one is going to be A band. The black line indicates A band because that's the thick filament attached to M line. The pink one represents, the purple one represents C zone, where there is going to be interlocking of thick and thin filament. And the blue region indicates H zone because that's a region which consists only of thick filament without any thin filament. All right. It's a sarcomere based question. And identify the region indicated by stars. The answer is going to be option 2, I band of this. Fine. That's question number 13. Coming to question number 14. Contraction of sarcomere. What happens to the area highlighted by black line when a sarcomere contracts? This is the black line they are talking about, guys. So here you are seeing the black line, the area highlighted by black line. What happens to this region? You can clearly see it indicates thick filament, and from one end of thick filament to other end of thick filament, the black line simply indicates A band. And you guys know this very well. During contraction, A band is going to remain the same. It is going to remain the same. And which gets shortened? I band gets shortened, which becomes completely disappears. H zone completely disappears, and nothing is going to get lengthened during contraction of a muscle. And hence, out of all the options, option 1 is going to be the best answer for question number 14. It is A band and it remains the same, guys. All right, that's question number 14, people. Coming to question number 15. It's a length tension curve. We again discussed this in classes. So you know that the force that gets generated out of a muscle is going to be maximum at what length? All right, necessary theory were printed in the notes itself, people. Let's get to the question. Length of sarcomere at which tension developed during contraction reaches maximum is going to be very good. It's going to be optimal length. Good. Optimal length is the right answer. And please remember, at this optimal length, what is the length of sarcomere? Again, this is something you already studied. It's just going to be a revision. It is going to be 2.0 to 2.2 micrometers. That is going to be the length of sarcomere at optimal length, people. That's question number 15, guys. Optimal length. Coming to question number 16. Here you are going to see a curve which is showing significant amount of contraction and there is no relaxation you are seeing. All right. So the strength of muscle contraction keeps on increasing without any relaxation at all, which means at this point the muscle has gone for tetanization. There is a prolonged contraction without any relaxation. This is called as tetanization. All right. Now, ion responsible for highlighted segment. This is the highlighted segment they are talking about in the graph shown above. Which ion could be the reason behind tetanization? So what is tetanization at the beginning? The muscles are going to remain in a state of complete contraction without even a speck of relaxation, guys. And you know what ion is going to be facilitating the process of contraction? Obviously, it is going to be calcium, right? So calcium is the ion responsible for contraction. Calcium is going to be the ion which is going to be responsible for tetanization as well. Whereas sodium is for depolarization. Potassium is for repolarization. Calcium and sodium not possible and hence not a right choice. So all the other choices are ruled out. Calcium is going to be the right answer for question number 16, guys. It's the contraction leading to tetany.